Okay, today we are talking about polar coordinates and plotting within them and also just what they are, conversions. And then we're going to start taking it to another steps and we'll convert equations and do some applications. And then in 6.5, this is 6.4. In 6.5, we're going to talk about function or analysis on them. They're not really functions, potentially, some of the equations. So we'll do some analysis, talk about symmetries, and make some really cool graphs. So, um, polar coordinates. Remember, they are r theta. So looking at example 1, we're going to put a couple of these on a graph. 2 and pi over 3. 2, remember, is the radius. Pi over 3 is the angle. Pi over 3 is approximately 60 degrees. And my point is here. Ultimately, what I've got here is the point. Let's call it P. It's not the line to it. The line to it just helps me measure where it is. Okay. Just like we've been doing, positive angles go counterclockwise. Negative angles go clockwise. Finding polar coordinates for a point. This is going to be example 2, and this is going to be finding all polar coordinates, which is a little different. So we've got point P, and it's equal to 3, comma, pi over 3. So radius is 3, angle is pi over 3. Well, we know this is going to repeat every 2 pi. So it could also be 3 pi over 3 plus 2 pi, which when I'm adding 2 pi in this case, I need a common denominator, which is 6 pi over 3. So this is 1 pi over 3 plus 6 pi over 3 is 7 pi over 3. It could also be expressed in polar coordinates as going this way, but having a negative radius. So that's negative 3, 4 pi over 3. Or I could go the negative way for that angle. Negative 2 pi over 3. So ultimately, I can add or subtract 2 pi any way I want. So ultimately, my two answers are 3 pi over 3 plus 2n pi. Some people have said 2 pi n, same thing. And again, n is an integer. Does not have to be 0. That would be the pi over 3. So this little symbol here, this funny z stands for integer. I'm going to show you some higher level math notation. This is a little thing that says exists. So n exists in the integers, or n is a member of, is sometimes how it's said. I also must do my negative radius one, though. And I think I'm going to do the negative 2 pi over 3 plus 2n pi. You'll notice your book sometimes is doing a plus or minus in front of some of them. Pay attention to those because your coordinates could be both. Okay, so converting rectangular to polar. So if you've got polar, this is polar, standard coordinates are known as rectangular. And I've always encouraged you to draw the triangle. But you can also use these simple conversions. X is r times cosine theta, y is r times sine theta. Again, theta must be measured to the positive x-axis. That's the default for polar coordinates. Rectangular to polar. R squared equals x squared plus y squared. And I'm using the Pythagorean theorem here. And there's a reason I'm going to say this way. Tangent of theta equals y over x. I was tempted to say theta equals inverse tangent, but that doesn't really work if your point is over here. Okay. You'll probably get an inverse tangent that's down here. But if you want that, you must, if you get negative 45 degrees, and it's actually the points over here, you better tell me that that's 135 degrees. The tangents are the same when they're 180 degrees off, or off by pi. So we're going to do a couple conversions here. Actually, I'll leave it on that page. I'll just switch colors. Example 3. 5 pi over 6. So we're going to convert this to rectangular. So I'm over here. Again, my formulas work really nicely here. Pi over 6 there. And we can just do 3 cosine 5 pi over 6. It's negative 3 square root of 3 over 2. This is a 30, 60, 90. So I know that this is 3 over 2. And this is negative 3 root 3 over 2. And you could do, if you don't know that, these formulas are pretty straightforward. 3 over 2. So my coordinates, this is part A in example 3. Part B gives me something a little bit different. Again, I'm going to set this up. Negative 200 goes this way. That's 2. That's 20 degrees. This one is going to be one where those formulas come in really nice, because I don't know what that is. Make sure you're in degree mode. Here we go. So, oops, R. I know R. I should fill in R. It's 2. So there's my coordinates. I don't know. I'm forgetting parentheses here this morning. Negative 1.88. Y equals 2 sine negative 200. It's important to enter the negative part for these. 0.684. It's a point. So my coordinates are negative 1.88, 6.84. No, 0.684. Important that I don't change that. And there's my answer. So now we'll go the other way. Rectangular to polar. So we have r squared equals x squared plus y squared, basic Pythagorean theorem, and tangent of theta equals at y over x. So example 4 is going to go the other way. So negative 1, 1. This is part A. I'll put that on the graph. Negative 1, 1. This angle. Hopefully you can recognize that this interior angle is 45. And it wants these in radians. That makes this 135 or 3 pi over 4. So 45, 45, 90, so that's square 1 times square root of 2. Again, I could use the formula. And I get r squared equals 2, and r equals square root of 2. The radiuses are always positive, so I don't need the negative one. I looked at my chart and got my angle. So if I simply did tangent of theta equals y, 1 over negative 1, I will get for this negative 45 degrees, or negative pi over 4, which is over here. Because I made my graph, I know 180, that is 180 off. So that is important not to do that. You could also say, the other option here would be, you can take your angle, but then you have to offset the radius as a negative. Okay. If I want my angle to be down here at negative pi over 4, I can just make my radius negative square root of 2 instead of square root of 2. For part B, we're given negative 3, 0. Well, this angle here I can tell is 180 degrees or pi. Thus the graph becomes really useful. And the radius is 3. Or, and do a radius of negative 3 and an angle of 0. And sure, I could make any of these 3 pi plus 2n pi. Any of these could repeat. For the most part, we're going to do it the first time around the circle unless specified that you're not. Okay? So there are some things of equation conversion. Okay? So we will convert rectangular equations to polar equations. So here's my equation. R equals 4 cosine theta. I'm going to use all my conversions. I'm going to use some combination of these and these. So I do not have a nice thing to convert r to x or y. I'm going to convert this into rectangular form. I want to make it r squared. So in order to do that, I also, for cosine theta is not r, for r cosine theta is a thing. So I'm going to go ahead and multiply squared on the left side of the equation and a 4r cosine theta on the right. And I knew that x was equal to r cosine theta. And I knew r squared was equal to x squared plus y squared. So I have to think creatively to get to some of those four things that I know. So this becomes x squared plus y squared equals 4x. Okay. X squared minus 4x plus y squared, I intentionally left a space there, is 0. I moved the 4x to the other side by subtracting 4x from each side. And now I'm going to complete the square on x. We did a little bit of completing the square before. Most of these, they're nice and they don't give you a leading coefficient. So I need to complete the square, my middle term is this -4. I divide it by 2, I get -2, and I square it. And that is my magic number. And that's +4. Remember, if I add 4 to the left side, why did I make that a 1? This is a 0. If I add 4 to the left side, I must add 4 to the right side. So now I can go ahead and factor that into something squared. It's x minus b over 2. So -4 over, or x plus, this one was minus though, x plus -4 over 2, or x minus 2 squared. So this is a circle here, centered at 2, 0. Remember circles. Centers are HK. Radius is equals 2, because it's equals to r squared. So let's take a look at another one. This is going to be example 5. R equals 4 secant theta. So I know here that R equals 4 over cosine theta, because none of my conversions have a secant in them. I'm now going to multiply both sides by cosine theta and get R cosine theta equals 4. We know R cosine theta is x. X equals 4. This is just a vertical line. That was an interesting. This is a vertical line at 4 in polar form. Again, not quite what I would have expected when I looked at that, but that's what it is. So we can also convert from rectangular to polar, which can be a little bit more complicated maybe. Okay. So here we have a circle. We'll just take note that the center is 3, 2, and the radius equals square root of 13. Okay. Then I'm going to show you how to graph the polar form on your calculator. So first thing I need to do is I need to expand this out. Remember, x minus 3 is not x squared minus 9. I must FOIL, but the shortcut is x minus 2 times 3 times x. So I multiply both of those and double it because they both get multiplied when I do that. Plus 4y plus 4. I'm going to subtract 9 and 4 from both sides, which is essentially subtracting 13. So that gives me x squared minus 6x plus y squared minus 4y equals 0. I think I'm going to move the 6x and the 4y to the other side. Try to make this a little cleaner. Now I'm going to use some of my formulas for conversions. I have r squared here equals 6 cosine, no, 6r cosine theta plus 4r sine theta. I probably shouldn't have moved them, so I'll move them back. So we can factor out an r. All of these have an r in common. So I know if it equals 0, one of my two factors equals 0. This one, r equals 0, that's not really valid. That's a single point at the origin. That's not what my circle is. This other one, though, if I swap things back over, r equals 6 cosine theta plus 4 sine theta. Typical polar coordinates are in r equals form. So that is my polar coordinate. Sometimes we'll express theta 0 to 2 pi. They're giving it or equal to. You're really getting a repeated point at 2 pi, but that's kind of helpful sometimes. So make sure, especially when you use the calculator, that it gets all the way there. So I'm going to show you how to graph this on the calculator. So we haven't graphed polar coordinates on the calculator, and we absolutely can. Clear this out. First thing we have to do is we have to go into our mode, and we have to switch function. We've done a little bit of parametric graphing on here, but there's parametric mode, and there's a polar mode. The sequence one, we probably won't really use this year. Now when we go to y equals, we get r equals, and our x variable is now a theta variable. That's why there's a theta. X or t for parametric or theta for polar, or n is for sequence. I think I can just go to zoom standard here. Now, it looks like an oval that is probably the fault of the zoom here. I'll change that in a second. But if you'll notice, these one on the X is bigger than one on the Y. So you won't get a very good circle when your things are not spaced evenly because your shape is not a square, it's a rectangle graph shape. So we're going to do zoom square, and that'll make each of the X's and the Y's equal. And if you'll notice, now it looks like a circle. It does look to have a center. I believe it was 3, 2. Yes, the polar graph still shows rectangular grid coordinates. I don't love that, but it does graph it in polar pretty nicely. I believe this was supposed to be centered at 3, 2. That looks about right. That is the nice thing about here. You can see the rectangular conversions. Clearly, we have now graphed something that is not a function. If I had wanted to graph that before, I would have had to graph a plus or minus square root because everything has to be in y equals form. And you have to graph the two pieces of functions separately. Okay, we're going to do a little application here, and that will be our last example. That's example 7 from the book. And this is actually an application of polar coordinates. It's a real one. Radar detects two airplanes at the same altitude. Their polar coordinates are 8, 110 degrees, and 515. The question we're asked is how far apart are the airplanes? So 8, that's 110. For here, we'll do, I'm gonna circle this in red. 5, and that's 15 degrees. And I'm really asked how far apart are they? That's this. Well, if I want this angle here, I simply do 110 minus 15, and that's 95 degrees. This, the distance, I can just use the law of cosines. D squared equals 5 squared plus 8 squared minus 2 times 5 times 8 times cosine of 95 degrees. And then I'll square root all of that. So I'm just going to enter that into my calculator. Or I'll do it on the calculator here. I'll get out of this. And yeah, I'm just going to do the square root of what I just entered. Oh, I'm in radian mode. Looking at the top of my screen, it says radian. I'm going to need to change that here. It's probably because I'm in polar graphing. My answer wouldn't have made sense. I would have checked, but it's kind of nice with these CEs. You get this right here telling you your modes. And so I've got it, they are 9.79, 9.8 miles apart. Assuming these are in miles. Yes, unit does say miles. 9.8 miles is the distance between the planes. Okay, that is polar coordinates.